Don't ask about this monstrosity which I hold currently. I'm a genius, okay? Back in the days when the Unreal Engine 5 trailer came out, everyone was so hyped because of this, and this, and for some reason, this. I mean, what am I looking right now? Is this noise?
No, those are individual polygons.
Oh, now I understand. This is pretty cool actually. This trailer showcased many new and exciting features of this engine. It felt like we are stepping into a new era of gaming where we can have millions of polygons on a single object while having fully realistic lighting. There was one problem. I was not interested at all. So to understand my point why is this happen is because at the time I was strictly interested in VFX rather than game development, and for me this amount of polygon is just simply a regular Monday morning. Turns out that this engine became the VFX nowadays, so I was wrong. However, there was something that caught even my attention. Hey guys, Reactive Andrew here. Today we're gonna check out this new Unreal Engine 5 official PlayStation 5 real-time tech demo trailer. So far, for me, real life looking much better than this. Even if I haven't left the house since 2011, I haven't touched grass since then, so it's not that big of a deal for me. I see some balls hanging around. Yes, chat. Oh wait, that's looking interesting. Wait, chat. Oh, what the hell? Chat. Is this real? This is unreal. This is actually unreal. Look at that. When the light hit the insects, they're running away. That's unreal. And chat. Okay. Stop this. Look, almost there. We're almost there. You see? Those are running away. It's super cool. This effect was so intriguing to me at the time that I wanted to recreate it in Houdini. Back then I was just a level 1 Houdini noob, but with a few weeks of research and development I was able to recreate at some level. Then why does this video even exist if I already done this years before it? Well, the first system had some flaws. For example, the entity is not pushed away to the closest dark spot, but rather just the edge of the light. That's because the vector which advex the insects is calculated by the center of the light minus the closest illuminated spot to the insect. The outcome of this calculation was a radial layout, where each vector points outwards to the center of the illuminated area. Because of that, when there's an object which goes a shadow, the crowd don't detect that as a safe spot, so they still run to the edge of the light. Oh, and I forgot to mention that this is the last evidence that this setup ever exists. I don't have the work files anymore, so I need to remake the whole system from scratch. But before we jump into the actual project, wrap up what we can see. At first, you might assume that each character is hand animated, but that's not the case. What we are seeing here is a process called crowd simulation. It's the process of simulating hundreds and thousands of entities at the same time without the need to animate each of them separately. Unlike traditional animation, where the artist must animate every character in a scene, crowd simulation only requires animating small behaviors, such as walking, running or idle. Then, we can store those small animations, also known as clips, for each characters, and can be used to represent different states of the individual characters, also known as agent, in a simulation environment. The main reason why this technique is so popular is the cost effectiveness. With crowd simulation, you can simulate millions of entities without the need to hire a large team of animators. However, there are some downsides as well. Unlike traditional animations, where the artists have full control over every actions, crowd simulation can sometimes behave unpredictably. Agents might walk through on each other, pick up strange forces, or ended up in awkward positions. Despite all these challenges, crowd simulations are widely used, not just in CGI, but also in various other fields, such as urban planning, emergency management, and even by military forces. It's also important to keep in mind that not the whole agents get simulated, those are just shell, which just get instanced to a point which stores all the actual information I just mentioned previously. So at the end of the day, crowd simulation is just a particle simulations with extra steps. So in a video, I'm often gonna refer these as just particles. Now, let's take a look at the demo itself. What we can see is the insects crawl around the environment. Sometimes they stop for a few seconds, then start crawling again. We can model this behavior pretty easily. First, we need to create two states, crawling and idle. Let's assign these two to every particle in our system with a random distribution, then during runtime switch between the two after it's been in that state for the given time, plus minus some time offset. The tricky part becomes once an entity gets illuminated, at which point it starts to escape that area. Every insect, no matter the previous state, must switch to this new one in this case. Call this one panic, which we can build up by the following rules. It's using the crawling animation, the movement speed is increased, and last, it's tried to move as fast as possible out of the illuminated area. I'm not sure how they manage this in Unreal Engine. My guess is that the light and crowd system can communicate with each other during runtime and share information, such as where the surface is illuminated by the light source. Now, this is a problem, because unlike Unreal Engine, Houdini handles the render and simulation at different times, so we are not able to interchange information in such a way. The closest we can get is to estimate where the light is going to hit the surface and use that information to drive the simulation. To calculate this, I need to create a light source on steroids. For this, I grab the spotlight and a really high-res sphere. I copied the location values from the light to the sphere, which means that these two are going to stay together till the end of the universe. Next, I created the normal for the sphere and kept only the points. These points are going to be our photons, and because the normals are pointing outwards, it's going to have the same general direction as our light source light rays when we hit the render button. But we need to filter out most of the points, because 90% of them do not represent where the light source is going to project the rays in the render. To achieve this, I use the same tactics as previously, but with a circle. And instead of just copying the location values, I copied the location, rotation and Coon angle. Now, if I project the photons to this circle, we get all the points which actually represent the spotlight's illumination. And because I still have the normals for all the points, I can do another projection, but this time to the actual surface, to get the areas which are hit by the light. As you can see, we have a pretty accurate representation. And it's great, because unlike the render time light rays, these points are available at simulation time. For the next step, I convert the surface to a point cloud and transform the color information from the projected light points to this new point cloud. Now we have two streams, one contains the dark and one the light points. I grab the light points and convert them to a blob, which I'm going to use to switch the state between the panic and crawling, and put this aside because we don't need this at the moment. Then I jump back to the two streams. Here I do the calculation to get the closest dark point for each light point. To achieve this, I use the nearPoint function, which returns the closest point from an input. Now, I have the closest point for every light point, and with that I can grab the point position as well. Once that's done, I just need to subtract the current point's position minus the target point's position, and normalize the result, just in case. The result looks pretty rough, because there's a bunch of points which have the same closest dark points. To fix this, I add some blur to the result, so it looks more natural. I also noticed that sometimes the vector's direction is pointing outwards from the surface. That happens when there's an angle change on the surface. I was worried that this would send my insect to orbital, but I keep continuing and worried about this later. Now, I have the light points with the proper directional vector, but this will still useless information for us, because we need to convert this information to something else, which the solver can use to update the direction and velocity of our agents in the simulation. In the DOP context, there's a node called popAdVectByVolume, which gives a particle a velocity based on the volume field. And because a crowd simulation is a particle simulation, we can use that. And we also have all the information to create a volume. So I grab the previously made blob and the points with the directional vectors and combine them together to make a volume which stores the calculated normal direction. Wait. You don't know what a volume is? I mean, if you're still watching this video, you probably have some understanding about volumes, but volumes are an area in 3D space, which we divide into small cubes, also known as voxels. Basically 3D pixels. These voxels can store any numeric information. For example, if we store floating points in it, we can represent a fog or cloud. In our case, we are going to store 3 floating points in each voxel, which is going to represent a vector. And later on, in the simulation, we are going to use these vectors to move our particles. We are done with the illuminated area calculation, but before I jump into the crowd simulation, I need to create a character, so I don't end up like the last time. I jumped into Blender and rigged up the model and created some basic animation. like this beautiful walking and these idle animation. Chef kiss. By the way, the rig was so bad I was remade it later on and added a new cool animation where the cockroach do this. I'm not sure if they are able to do this. This is hilarious, but Google Docs tried to correct me when I said I jumped into Blender into I jump into a blender. First, I added the rig model to the scene as an agent and did some preparation on it. When you first import the character, it's just a packed geometry, meaning there's no useful information to the solver. To fix this, we need to convert each previously made clip into its own separated points. After all that, we can finally work with the simulation itself. I mentioned a few times, but craft simulation is just a particle simulation, so there's no dedicated SOP level node for it. So we use a plain DOP network and build up our system from ground up. I noticed that my insects are constantly running into each other, even if I try to discourage this behavior multiple times with different methods. Hey, post-editing me here. In this section I talked about how the small scale caused this issue. Well, it turns out I was wrong. Even at this scale the animation worked just fine. I just forgot to turn up the max angle turn rate. If I turned it up, everything's work as intended, so yeah, bye. There's still some collision here and there, but the result is just much better. But I was curious how they solved this problem in the Unreal Engine 5 trailer. Well, they don't. In fact, in that simulation, the insects are constantly running through each other. So, if the big boys and girls won't solve this problem, why should I care about it? So I leave it as it is and move on. Next, I start to work on the behavior of the insects. Houdini uses a state machine style workflow to build up the behavior tree, so I built up that system. But then, I noticed there's no way to set a random timer to the current state duration option, which means it switched the state at the same time for every particle, which looks kinda funny, but not what I want. But for my luck, another option, time, which did not work as I wanted, had a random offset slider. So it was time to dirty my hand and crack up the crowd trigger SOP. I extract the two options VEX code and try to find where the random offset is used in the time-based settings. I just paste that line into the state duration type code, and it's worked. So now each insect spends a few seconds on each state, plus random offset, before they switch to another. The problem is that in the trailer they do wide turns, while mine feels like they are skating on ice. That was because the crowd settings max turn rate is pretty low for what we need, because the default setting is designed for humanoid characters, not insects. So I just cranked up the max turn rate to 180 degrees and the problem is fixed. And we are finally done with the crowd simulation as well. They are running around happily, but
they don't know what is waiting for them.
The next step is to connect the two systems together and make them actually react to light. First, I added a new state to the mix called Panic. This is the same as crawling, but with a much higher warp speed. Once that's done, I created a new trigger to turn the insects to panic mode when they are inside the previously created blob, and then turn back to the crawling once they leave that area. Now, the problem is that they don't wanna leave. I mean, there's a chance that some of them are leaving by accident, but we need to force them to leave. And this is where our velocity volume came in picture with the previously mentioned pop advect by volume node. I plugged the node into the states and set the velocity field. And finally, they tried to escape the illuminated area. So far everything works fine, but currently we still use the testing flat plane, so the next step is to create an actual environment. I started looking for some photoscan that I can use. I ended up with this ruined house and this pile of rubbish. I just need to replace the grid with the newly created environment and set the terrain for the insects. And then everything's break. Particles clipping through the terrain, teleporting to random locations and doing this. Most of the problem came from the fact that the rubbish model was just simply too complex for this task. There are a bunch of small holes, pits and sharp angles, which the craft solver won't handle too well. In fact, if you take a look at the reference, most of the quote-unquote walkable terrain for the craft simulation is much more simpler than the actual render geometry. For example, those vessels is not part of the insect's terrain because they're just simply clipping through. Also, you don't see any situation where there's multiple layers of walkable terrain on top of each other, so I limit the scope and only work with the floor of the ruined house and leave the rubbish model for now. When I say it for now, I mean never put it back. I tried to make this work later on, but it's failed, so... I made a much more nicer outcome, and for the last step I rendered out the result. And with all that, I managed to replicate the insect light reaction in Houdini. For the last step, I do some color grading on a final render and add some crawling sound effect. And it's all done. I wrote the technical documentation on Medium if you wanna read more about the topic, or head to my Patreon where you can download the whole heap file with all assets included. With all that, thank you so much for watching and see you next time.